Arrival time variation. Variation in the on-time arrival percentage was analyzed for 21 time blocks accounting for every hour of the day at Miami International Airport and Fort Lauderdale International Airport. The standard deviation for MIA was 14.2 with a mean on-time arrival rate of 66.7%. The standard deviation for FLL was 12.5 with a mean on-time arrival rate of 78%. At the 5% significance level, test the claim that the two airports have the same variation in on-time rates. So this phrase, test the claim that I've underlined, test the claim that they have the same variation indicates we're dealing with a hypothesis test about the population variances. So let's express that claim symbolically. Okay, so the claim would be, since we're saying they're the same, that the variance for Miami is equal to the variance for Fort Lauderdale. Another way you could express this claim, if you wanted to, you could divide both sides by sigma squared f. If you did that, then we would end up with, sigma squared m divided by sigma squared f equals to 1. Because, of course, if you divide the right-hand side by sigma squared f, you would get the value 1. So some professors will express this type of claim in this fashion. I don't like to do that, so I just leave mine in the straight line like we've normally done. There's nothing different about these other than there's been an algebraic manipulation here to make it look a little bit different. All right, so let's go on and continue with HO and HA. Now, when the claim has an equal sign, we know the claim and HO are the same, so I'm going to go ahead and say that these two guys are the same thing. And then for HA, of course, it would have to express the opposite idea. So we're going to say sigma squared for MIA is not equal to the sigma squared for Fort Lauderdale. All right, now from there, we're going to list the data. So I'll list the data under MIA and FLL. All right, for MIA, it says that the standard deviation was 14.2. Now, as far as the n goes, you might say, well, what are the n values here in this problem? It says here that variation in on-time arrival percentage was analyzed for 21 time blocks accounting for every hour of the day at Miami International Airport and Fort Lauderdale International Airport. So the n for this problem is 21, actually. Okay, so those are the sample sizes for both groups, for both independent samples. Now from there, let's go ahead and take that and then express what else they give us in the problem underneath it. So it says the standard deviation for MIA was 14.2. Standard deviation means S, right? That's the sample standard deviation. So it's not squared. We'll have to square it in our formula later. The standard deviation for FLL was 12.5. And then it goes on to tell us that we have a 5% significance level. Now they gave us some information here that we do not need. They talked about the mean on-time arrival rates, right? Well, we don't really care about that for this problem. That's not our interest, so we don't have to worry about it. Okay, now from there, the next thing we want to do is to express our test stat as f equals 2, and we're going to put the top of the fraction as MIA because it has the larger sample standard deviation. So we're going to do s for m squared over s for f squared. Plugging in the numbers, we have 14.2 squared over 12.5 squared. We'll work that out. Let's see what we get. So we'll have 14.2 squared divided by 12.5 squared. When we hit enter, we get 1.290. Okay, so that's our test statistic, 1.290. All right, from there, what we want to do is to take that and look at our critical value, right? And compare our test stat to our critical value. So if I draw a drawing for this, draw a sort of skew distribution that represents the F distribution, a right tail, because this is always a right-tailed test. We're going to look at HA and determine if it's a one-tailed or two-tailed, and I see because of the not equal to, it's a two-tailed test. That means we have to chop alpha in half, so the F value that we're going to use here is going to be 0.025 for the alpha value, and then we're going to have degrees of freedom 20 for both the numerator and the denominator. Okay, so let's go to the 0.025 F table and look up 20 degrees of freedom for both the numerator and the denominator. Okay, so I'm on the 0.025 F table, and I'm trying to find degrees of freedom 20 for the numerator, 20 for the denominator. I don't see 20 for the numerator on this page, so I'm going to go ahead and go to the next page and see if I can find it there. Okay, so Now I see 20 here for the numerator degrees of freedom. Now I must scroll down until I get to 20 on the denominator degrees of freedom. So I see it here, it's 2.46. 2.46. Okay, so we found our critical value to be 2.4645. All right, with that critical value, when we look at our test stat, we see that it lands somewhere here in the do not reject HO region. So do not reject HO region. Therefore, do not support HA. All right, so when we look back at our claim, we see that our claim is the null hypothesis. So we're going to be using this phrasing here. So we're going to say the sample data does not allow us to reject the claim, right? The sample data does not allow us to reject the claim. All right, and so what this means is that essentially we cannot conclude from this data that there's a difference in the variances between the on-time arrival rates for MIA and FLL.